Hi, good people of Skellefteå. So today I came to the neighboring city to Luleå, to Skellefteå. So here we have a bunch of students, bunch of three. But I mean, first question. Are you normally three here, or there are more?
So
Huh?
it's usually that low.
Okay.
I think
But I mean, do you know each other? I mean, those who are here, and how many are you physically, like physically here? I know that there are some who are still online, but they are kind of registered in Skellefteå. So how many do you know? Eh?
uh,
6, 7. Okay. 6, 7. Okay. All right. So let me start. So recording is going on. Let me just switch off the telephone. Yes, let me see. Yes. Hi once again. So let me see if I have sound on the computer. So if you have questions online. So now I'm welcoming you to the second theory module. But before I continue, so I just want to ask, so how did it go with like the materials from the first module? Well, first I ask you, since you're here. So,
um, it's a lot of new stuff,
uh-huh,
and it's a lot, I think, personally.
uh-huh.
Yeah, I'm having a bit of trouble going through all of it, understand all of it, and then also doing the labs.
Okay.
Um, yeah,
Yeah,
so
the labs we will be talking about today with you. So, that's why I'm here. What about you?
mm, yeah,
Say again?
pretty much the same.
Okay. And what about you, my friend?
Yeah, having no experience in AI, and it's kind of new. Everything's new, and
Everything is new, but that's good. That's good. I mean,
yeah,
so then there's just spending your hours.
a lot of hours
Yes,
and a lot of
exactly.
knowledge.
Well, maybe I can start with the story. So, I once upon a time, so now I think it's about 30 years ago. So I moved from my home country to Switzerland, and so I was enrolled in a master program or pre-doctoral program at EPFL. So it's one of the top schools in Europe, and that was a program. So when I came, like every single subject was new. Yes. So basically, the only weekend we have, or we didn't have weekend. Well, the only free time we had like few hours on Thursdays because we handed in home assignments in the morning, and we got the new ones in the afternoon. So there's hours in between. So that was our 3 hours. So that's you're not alone, but I hope you will learn at least something new and useful. I know that it's pretty much the case, as I understand, even for people online. But that's not the reason um, to lower the ribbon, so to say. So we go as it is, then we see. Okay. So I hope you study hard and learn. And once again, this topic is super important. I mean, like it or not, we live in this really transformative times. I mean, this AI, it is everywhere. I mean, maybe AI is a little bit overused term, so it's buzzword. Like people talk about AI, this super intelligence and such. I mean, here, you need to understand AI in pragmatic terms, data-driven models doing something useful, and uh, so useful that that the whole industry is transforming. So self-driving cars and then so image recognition. So we reached the level which we never experienced before. I mean, it's not happened overnight, but definitely within the last decade, there was a revolutionary step towards capabilities of models, and especially, I mean, when this Gen AI came along, so it became a kind of enabler for integrating all this different stuff. But then again, I just want to repeat it once again. It is almost like with social media when they appeared, or smartphones. You know, when a new technology came along, you really not equipped with skills of using it right, or not being even aware about pitfalls of using them. So, and I apparently, so it took all these tens of years until last year, 2024, when first normative act, so we will be talking about this EU AI Act, was finally accepted. So it went through all the parliament hearings and such, and it was signed by the members. In simple words, what is it all about? So it's the document that regulates usage of data-driven models in different kinds of applications. So, and of course, there are less critical, there are more critical, there are super critical applications. And then again, so we are talking about applications with a high level of criticality. So when machine learning model is inserted in life critical loops, control loops, again, image recognition in self-driving cars. So you don't want a car to hit someone just because few pixels was modified on the camera or something like that. And again, apparently, my message from the last week is that, well, AI is about math. Yes. So you were exposed, maybe for you, I mean, if you didn't deal with it before, so it can appear a bit overwhelming. But that's the core, the heart of current AI. I mean, the way how you take the model, you shape it. So doing pre-processing, that's what you did in Lab 1. You input into a machine learning model. So, and there are different kinds of machine learning models. We are concerned about artificial neural networks, which are, again, I mean, the variety of them is really high. So I'm not even, I don't even want to start speaking of taxonomies. But the principle is all same. It's a backprop model. So it is the well, let me just skip it to this slide over here. So it is about inputting a data and passing it through a cascade of mathematical functions. So very simple mathematical functions. So basically, each and every circle here is a weighted sum. So, and what it does, again, on a hand waving level, so it piecewise approximates the border between the data in a representation space of certain dimensionality. Again, maybe it is hard to imagine. I mean, dimensionality is more than 3. But again, so you should tune yourself to this geometric view. So your image, whenever you see an image, like you worked with MNIST dataset number 7, it's 784 pixels. Well, they arranged in the grid so that we perceive it as a 7. But it is 784 values. And so as such, it's a point, it's a single point in 784 dimensional space. And now, again, so you should, well, I guess intuition here works pretty well. So you should understand that all sevens having this pattern of illuminated pixels, they group here. So there's a point cloud. So all ones somewhere close, because I mean they obviously correlated. Maybe eight a little bit apart. But again, apparently, if you would visualize it, so there are different visualization methods like TSNE, for example. So you see all these points are very near each other, and sometimes they overlap. Uh, and uh, and again, they overlap when they, I mean, when they are projected, I mean, to something digestible to us. In reality, still there are gaps between them. So, and what machine learning models do, so they try to find a way between these clouds. So it's kind of funny, I mean, if you think about it. Um, and the way how you do it with artificial neural networks is by using this piecewise approximations. Well, they are not linear piecewise, but non-linear piecewise approximations. So step by step, you draw a line between two point clouds in high dimensional space. And of course, we are not talking at all about how to choose the numbers of these parameters optimally, but there is a science behind it. So how many, well, input is something that you deal with. So this is, for example, resolution of your sensors. At some point, you can reduce the dimensionality. So that's very one of typical steps. So you probably can do pre-processing and remove some, say, pixels that for a given data set are not significant. So that's there are methods for that. But nevertheless, whatever is significant and meaningful, you input and you pass it through this network, which what you have to see, and that's what I will what I did use last time and what I will use today. It's a single function. It's f. F that takes an input and produces an output, and an output is a label. Again, not a label as a letter, but I mean it's a number. So you turn labels into numbers. So, but at the end, it's a pretty much standard function. The only thing is that you cannot write it down like in a closed form. But since it is approximation of this complex phenomena, so again, so in mathematical terms, all these point clouds, so they called well manifolds. It's a shape. It's a geometrical shape in many dimensional space, and you don't know it's a very kind of sophisticated shape. Yeah. So. Yes, and this whole construct is just approximate well builds this boundaries. So uh, that a term that we also will use later on. Yeah, and here from the point of the attack, one can have different choices. Obviously, sometimes. And this is the case, for example, for open source models. So it's very obvious so that people let models freely available. Like most of Gen AI models, well, not most, but many mainstream Gen AI models of older generations, they are free of charge, accessible. So ResNet that you presumably used in the lab, that's free of charge. Many pre-trained models are available. So what you can take it and start to analyze it. And as I said, so that's super predictable. So one of the, I mean, whenever you think about this machine or AI. When you hear AI, so there is no magic. So it's all math. And as I said, it is about a function estimating the boundaries between these cloud points. And if it is a math, then you can reverse engineer it somehow. And so all these attacks is about understanding. So understanding how to hit these boundaries with specific inputs. Again, so it's I mean, to imagine you can easily imagine it. It's not a rocket science. So you try to so you have this point in the high dimensional space, and now what is the attack? The attack is that how can I modify this point so that it actually crosses this line? But still, I mean, it appears kind of same. And that's what you work with mainly in this course. So you tried white box model. So when you basically analyze the gradients, so how this gradients, during the optimization process, so during the estimation, propagates back, and you use this information to actually modify the input. So you basically change intensity of certain pixels, and then suddenly it produces a wrong classification. And so as a kind of extreme case, so that's not a practical attack maybe, but you tried this one pixel attack. So the one pixel attack, well, to begin with, it's a black box attack. We will talk about it somewhat more now. But it is a kind of, I mean, well, it's a practical attack, but in the first place, it is attack showing feasibility of how little information you can change to actually trick the model. Yeah, but you do it, I mean, in the one pixel attack, you kind of, the approach is to optimize um, the search time. So you have in principle you need to try all the possible combinations, which are many. But I mean you have this evolution in the algorithm that hopefully will converge to this single pixel that needs to be modified. In the first half of this class, I want to talk about black box attacks in general, and then I want to introduce a new one, which is called the boundary attack. So, which is more, I would say, mathematically sound, and then you can easier to imagine with respect to knowing how artificial neural networks work. So, which is in contrast to combinatorial search of one pixel attack, which is optimized by evolutional algorithms. So this type of attacks targets the cases where you don't, where the model is proprietary. So you don't know the weights, you don't know how it was trained, but the only thing you know that it was trained using the well-known technique. And as such, so you know that I mean what model does it uh, estimates the boundaries between points on this space. And what you do here, in general, in black box attacks, again, so you tried it on one pixel, so you try to guess. Okay, so you try to guess about these boundaries. So by presenting examples or querying the models. is this model, is this example correctly classified? Yes or not? And in this way, you try to find out how to make an example such so that it is misclassified. And there are obviously um, different types. I mean, you can achieve the same goal in different ways, but the common to all these attacks is that so what you can do again, so you can send a query, observe the output, and in many cases you can even well, in some cases you can access the probability, so the output of the last layer. But for you, it's really a black box. You don't know the parameters. You don't know the training data. So you may know the domain from which it was taken, but you don't know training data at all. And but again, you know that it is trained using some common model, using common algorithm. Um, So again, having this understanding that all AI products are mathematical functions, and knowing that it is learned by propagating gradients, so you can assume that these boundaries can somehow be inferred. So and that's what is the kind of target of all attacks, to infer the boundary. You also know that what you also know as an attacker is that all data that is used for training a specific model exhibit one or another statistical irregularity. I mean, of course, I mean it should, because otherwise it will be random. So you know that certain phenomena are kind of follow certain statistical principles, and as such, in principle, you can understand the underlying statistics again without observing the true data. And another thing, so what is pointed out by the last item is that I mentioned it during the first module that the same task can be learned in variety of ways, using variety of algorithms. Like, for example, you tried this very simplistic KNN. It's a model. It's a classification model. Given a data, you can do predictions. And there are tons of algorithms that do, for example, designed for solving classification task or regression prediction task and such. What you can do, so without knowing the true model, but maybe having access to certain samples of data, you can train what is called surrogate models that you can build. And based on observation of how they do, you can figure out how to tweak the original model, So that's this type of attack is called model inversion. Yeah, so the state-of-the-art black box attacks, again, so you started with the principal attack, one pixel attack, so the general categories are decision-based attacks, that's what we will talk about now. Score-based attacks, so it is when you target, so you can observe the scores, when the predictions, and you target the attack to modify the scores. So understanding the confidence intervals. So how sensitive are scores for classification of one or another class, and then transfer-based attacks, as I have already talked about. So let's talk about decision-based boundary attack. So that's I found as one of the attacks which kind of, again, easy to understand geometrically, and again, based on the principles that you want to infer the boundaries between the cloud points. So what we do, again, so I will show you some slides with mathematical equations, but you probably have read them before the class. But also I will try to draw a geometrical interpretation of it, so that to clarify on an illustration. So, but again, just for the sake of terminology, so X here is our original input. For example, an image. If you are about targeting image classification model. This X so it's an adversarial example. So it's something that you want to craft so that your model produces wrong results. And you want to craft it such so that it is as close to the true example as possible, but produces a wrong result. So that's what's written in the goal. So the third bullet point. And the boundary attack. So again, so on the level of definition, it consists of two steps. So first, understanding the direction from the generated adversary image or sample to the true sample. Being able to take an orthogonal direction from this direction. So I will illustrate it on graphically, and then move it closer again. So you want to make it dissimilar, so not looking exactly same as the original input, but still kind of close. So it's an this is your optimization task. Maybe I can show you this illustration, which I meant. Oh. Oh. Just a second. I need to double check the Wi-Fi. Settings. No, it's not notebook settings. Yeah, it's here. Wi-Fi. What is my Wi-Fi connected? It's connected now. Okay. No. So let me show you. Let me see if I can illustrate it correctly. So uh, we take a simplistic example where you have two features. You remember, I mean, so in machine learning, our data, uh, each and every data kind, we talk of it as a feature of a phenomenon. So, and we have two of them. And why two again? So because it's easy to illustrate graphically in two-dimensional space. So and then we take a point. So somehow we get an access to, or we just um, we found a valid example. How you can find? As I said, so sometimes you don't have access to data, but you know the domain. So you can just take any input, I mean, from the internet, or you just guess. You pass through the network and say, okay, yes, it classifies as the valid example. And now this becomes your target. So that's X. So so feature value of feature one here and feature value. So one here. So far so good, right? So this is your X. Now uh, you want to come up with an adversarial example. So that's what you did in one pixel attack as well. So but there you just selected some pixels and started to modify them and test. Here we take a different approach. We generate a new sample randomly. Again, so at this step you can do you can have several heuristics, but so you generate a new sample which is X and so randomly. So and the thing is that I mean this randomly generated example. So what you can think about it, you can think about adding noise, lots of noise to your valid example. Or you can even just present a random noise to a network. So that in this case, your X alpha would be like very far away from the true image. So there are different strategies of starting choosing the starting point. And then that's what you do actually. So you know that a model it it has a certain decision boundary. Decision boundary that. So let me see. So after the training, so this is the boundary which decides whether this particular X is a dog or a cat, so to say, right? And the thing is that what you try to do, you try to move along, or you try you want to figure out. Let me just draw firmer. You want to figure out this line by moving by a process that somehow moves this adversary point closer to the original one. So you minimize the distance between them. So basically, you want to end up somewhere here. or yeah, let's put it. Let's put it here somewhere. So that's your so this distance, so this is your so that was the equation x odd minus x. So this is the distance you want to minimize. And you will do it by kind of at this at the one hand, you move to you move away, not away, but you move in the orthogonal direction from x, because if so that the intuition is very simple. So if you move always this way, so you you kind of make x odd more and more kind of alike with x. So I mean, so you basically this point will be wrong, so to say. What you want, you still want to kind of to have a strong case where the changes are significant for misclassification, but still kind of the point moves closer to the examples of the true class. And you do it by, as I said, so defining the direction. So first you define the direction D. So D is direction from x on to x. So you can define it. I will show you now the formula, so, but I just want to show you graphically. Then the process for the process for generating new samples of the adversarial example is to add noise to it. So you add noise so that you try to produce a new point somewhere in the vicinity. So say you choose this point over here. And now you want to create a mechanisms that kind of do this stepwise movements. So from here to here, from here to here, etc. So until you basically come closer to the borderline, and you are you understand that you come closer to the boundary by checking the classification, of course, on the example. So so what you do, so this point over here is x odd plus some noise. But this one, the vector, so this is the orthogonal to D direction. So that is this arrow here. This arrow is alignment with direction towards X. Okay. So what you do, you generate a point randomly, and from this random point, you also kind of choose more or less random direction. But I will show you, so by two steps, two mathematical equations, you can extract the components that enable these movements orthogonally from the direction towards X, and then alignment so that it still moves towards X. And in this way, so you kind of find eventually the intersection with the boundary. Yes.
And I have a question here.
Yes, sure.
Can you turn back to the picture, to the drawing?
Oh, of course.
Yeah, so I mean, here, why don't we just like, why do we generate the next X randomly? Why don't we just move along the
You don't
vector D?
um well, you actually that's what you do, but I mean you cannot say. I mean that's what you do. Essentially, you move, but I mean I can probably turn this your question back to you. So how would you generate this point? So you want to have principles that you want to have differences from the original data, but still, yes, it should move towards the original data. So
Yeah,
if you just move along D along this the from adversarial, so you kind of end up with the original data. You don't want to end up with the original data. You want to make it closer to it, but not exactly like this.
I think like if I'm just moved along, let's say vector D, right? So let's say that before I cross the boundary, the decision boundary, the model would still be able to say that the X adversarial is not classified as an expected class. But we will see that the probability will getting closer and closer, and we just stop when it's right next to the boundary, or like it's crossed the boundary, but right, yeah, at the right moment when it crossed the boundary.
Maybe you can do that. I absolutely. It's more your attack is then more kind of deterministic. And biased to this particular X, so to say. Maybe it will work, of course. But so here we also introduce non-determinism in generating the adversarial example. So that's at the end, so that point that we have, so it's found in a non-deterministic way.
Okay, so like we don't know if the probability getting increased or decreased during the finding of the adversary. Yeah. Maybe just one last question.
Yeah,
so let's say that we follow this strategy, right?
Mm.
And I suppose that we will end up having the X adversarial with one feature is really close to the real X. So in this case, I think feature 2
Yeah.
of the X adversarial is really close to the real X,
Yes.
but feature 1 is quite far away.
Yeah.
Yeah.
It's okay.
So
It's not a problem. I mean, you still achieve the goal.
Mhm. But I mean, like, for example, if like for picture, do we need to determine in advance that which feature that we could compromise that we
Well, I guess, I mean, there could be different strategies. Yes, I mean, you can restrict maybe the regions. I mean, yeah. So there are no kind of rules written in stone how you perform the attacks.
Okay. Yeah, understood. So this is just a strategy, and
Yeah.
up to the kind of application or
Yeah.
target, then we can
Yeah.
adopt it. Yeah.
Yeah.
Okay, thank you. Yeah, that's answered my question.
Mhm.
Yep.
So just to complete, this is the let me just this is the equation to determine the direction. Again, from the basic geometry. So this then we generate a random noise, so a random noise vector, so which we will add to the adversarial example later on. But again, just to recapitulate that this noise vector, so it can be it can point in any direction since it is random with respect to the to the target to the original data. So what you want, as I said, you want to have this kind of stepwise process of coming closer to it, to the decision boundary, and you do it by first determining the orthogonal direction, and that is done by, again, so this is a projection equation. So this is a dot product multiplied by the vector of direction. And then, so I can probably go back a little bit here. So what is going on? So you add, so you generate R, so here, so that's a random noise somewhere. Let me just maybe zoom in if I can. Oops, that's too much. Yes. So you have a R, so it points. It can point to different directions. What you do a projection. So you find this component that aligns with the D, and then you subtract you subtract it from it. So that you move a little bit. You move in the orthogonal direction. So that's the meaning of this step over here. And again, so I will not verbalize, so I try to put the explanations in text, so you can read it offline. But that's what you do. So you take your adversarial example and you move the you add a noise in the orthogonal direction to the direction towards the original input, and then in this step, so you actually move it closer to X. So you enable the move down. So and this is a kind of weighted average. So of this new adversarial example, and then you add a little bit of the true components. So if you think about, so it's not, it's quite intuitive. I mean, those are simple steps. And this is like putting all the pieces together. So the main update equation. Right. So let me see. Let me see. Let me see. Uh, the defense mechanisms. I will again. I listed in the slides to follow. So I listed some of the approaches. What you can importantly you have to get for yourself is that there are mathematically sound approaches, so it is meant that you during the training. So if I now go back to if I want to if I may use this uh, figure over here. So during the propagation of gradients, so the backprop, again, that what you tried in lab one, part one. So you not only just kind of when computing new weights, you remember, so you have this learning rate and the gradient, and you move it in the opposite direction of the gradient. So when creating a new weight. So what you do, you want to make so basically this mathematically sound protection techniques is to enable training with some boundaries on the weights, so that they tolerate these deviating examples. So you do on the one hand, the attacks turned into the defense by themselves, so that you do create adversarial examples, but then you also kind of train the network such that your computed weights tolerate these deviations. And this is, and if you do it with predictable tolerance of weights to this deviation, so that's called certified methods. Then you can do empirically. So you can try, again, you just train on adversarial example. So you see that, okay, so it works. So that's also could be a case. And there are combined methods. So the problems with defenses is that adversarial examples, so they appear, new adversarial examples appear, and methods for their generation. So especially for large models that requires time to train. So that's creates an issue of effective adversarial training. Yes. So let's now switch gears towards a different topic, the problem of privacy in AI technology. So if before we were concerned about the quality of the model. So that's
Thank you, Roman.
Yeah.
Stress level is getting high. I don't know, maybe between 6 and 7. Anyway, but yeah, there's capacity, so we will move on. What I want to share, yeah, we have started the new cluster rollouts, and then we've started with setting up. So we've been doing a lot of work from last week, and today we are going to see where we stop. Yes, I pass to.
I'm sorry. Was it a comment on this course or what? Or you just
I
didn't
don't think so.
or you just didn't mute yourself.
We will just manage. So I pass to
I think it's on different.
Clara.
It's a different one, not this course.
So that was a bit confusing.
Yeah, I think his mic was open.
Okay. The level of stress is high. Yeah. Okay. It increased my level of stress, you know. Okay, but I can deal with it. So let me see. So by the power of God, I mute you. Okay. Yes. But okay. So now I need to turn to to the problem of privacy. Yes, privacy. So that's a very important question with machine, or important problem, an important risk with AI technologies. So previously, we started a general class of attacks on data-driven models, where we attack the quality of the model, so the output of the model. So we want to compromise a model. But if you think about it, I mean, the key word that it is a data-driven model means that we build our models based on data. As simple. Sorry for the tautology. And in many cases, so these models that we build on, so they carry some sensitive information, whether it is sensory data from some proprietary sensors. Like, I can give you an example. If you work in a mining industry, so they have different, they have or mining or railways industry. So they have different producers of sensor equipment. And each producer, so they keep the data for themselves. Also, I mean, obviously, so it's not a private information in this sense, but it's very sensitive information. So basically, based on this data, you can infer, for example, the quality or the status of a particular functional block that the sensors monitor. So, and then of course things become more critical when we build models based on personal data. So like medical applications, whatever applications that require private information. So again, so I think I shouldn't spend more time on saying how critical this problem is. And in this module, I want to focus on two basic categories. We want to protect privacy of the data and the privacy of the models themselves. So again, these are two different angles. Preserving privacy of the data means that you shouldn't be able to identify data which was used for training by observing the input-output. So that's and again, so this problem appeared long before AI technologies became mainstream. So I mean, anywhere when, for example, people traded private data, so there was a need for anonymization. So and obfuscation, so hiding the information, but preserving some useful properties. And then I will be talking about privacy of the models themselves, in the context that you want to train your models on some untrusted computer platforms. So that's a slightly different angle. So here, let me see. I want to make a pre-announcement. Basically, here. So on Wednesday, the focus of the Wednesday class. So there won't be any class tomorrow, but on Wednesday the focus will be on membership inference. So, and it will be a guest lecture given by my colleague from RISE, which is the Research Institute of Sweden, working closely with privacy and membership inference. So the problem there is that how to ensure or certify that a model that you create or somebody else create doesn't leak personal data. And so there are several ways of testing it. So basically, you can try to guess. So one of the problems, concrete problems to solve, for example, is to identify whether a particular example was used during the training of the model. That reveals lots of information. And in the lab too, you will work with one of these methods. So whatever information comes on Wednesday, so it's relevant to practice too. So in what follows, so maybe I will do in a very fast forward manner overview of the mainstream data anonymization techniques. And as you understand, so these techniques are intended as a countermeasure to to prevent leakage of some personal data. So basically, what you can do, at least, you can pre-process your data and hide away reduce the determinism. These techniques that I'm saying, they do not guarantee that membership inference attacks cannot be performed. So it can still be performed, but at least it will somewhat minimize the risk of revealing personal data. So data anonymization techniques. So there are several options here: suppression, generalization, perturbation, and k-anonymity. K-anonymity is a more generic approach, so which is achievable. So it's more of kind of formally stated property. So what does it mean that a data set possess anonymity properties of certain strength, which is k? The way how to achieve it, so it could be by combinations of different methods from above. Again, so you can trace this example. So this example is very straightforward to understand. So this is your original data set with categorical features. Categorical means that they have discrete values, each feature. And we want to anonymize it somehow. So in suppression, you remove certain attributes or entire records from the data set. So, for example, you can remove the names totally and the zip code, so the location information. In generalization, again, so well, I like to put it more formally, but in the method itself is very easy to understand. So you substitute the exact values with the range of values. And again, you can do it in practically in different ways. So whenever you come to the point, so you can, and there are standard libraries for this. So you can, like in this example, for example, you remove the exact zip code and place a pseudo identifier of an area, and then you exchange the exact values of age to age range. So the idea is that you by removing this information, you still preserve the properties needed to build data-driven model. So you preserve the statistical properties of the data set. So k-anonymity in this case as I said, is a requirement. So that by the result of anonymization, every combination of values appears at least k times across different subsets of the data set. So this is an example of two anonymity data set by when you group the records with the same age range and gender and the area. So basically before, so there were several records. So here you you group them together by this removing the exact information about patients. So the important message to you with the anonymization or obfuscation, and obfuscation technique is about adding noise. So what you can also do, so you can insert noisy information into a data set or in the values, so that in a controllable manner. So that again, it preserves the properties, but I mean, the numbers that appear after obfuscation has nothing to do with the original data. But the result of the data-driven model is as if you would build a model on the original data. The important message here with anonymization and obfuscation techniques is the loss of utility. So what does it mean? So by all these methods, you reduce the quality of your data set. So you diffuse the point clouds, so to say. So and as such, your by definition, your model become maybe less precise. Or at least in the context of privacy preservation, it is formulated as optimization task. So you do anonymization, and at the same time you try to train the network to improve the accuracy, I mean the performance of the model. And again, with these techniques, anonymization and obfuscation, still you do not guarantee that, for example, membership inference attacks cannot be performed. And what would be an example? So you will learn more about membership inference, but it is very simple. So I mean, if an attacker wants to, so for example, in Sweden, you can get hand on a personal number quite easily. So you want to see, so you know something about a person, and you want to see whether it was used for training the model. So that would reveal quite a lot of information about the sample of data that you used. So you can try and test, for example, the data of particular individual that you access, whether it is present in the model, in the training set of the model. So there are different techniques for the training of machine learning models that can be applied to preserve the privacy, so to say. So what I talked about during the discussing the anonymization techniques. So those are techniques directed to modifying the quality of the data, which is used for creating models. What you can do, for example, you can modify you can modify the way how model look like after the training as well, so that you can for example make it less obvious to test to infer the presence of particular data. So the techniques here include, for example, model compression or quantization. So and it is about changing the weights, which probably appeared as a result of training on exact records, so without any privacy preservation techniques. But then you would modify them. So you would modify the weights such that they appear as different numbers. So they still work on the original data set, but it is harder to deduce the exact values which was used for training. So the last topic I want to touch on for today is learning on untrusted computing platforms. So here as I said, so we look at the problem of privacy or even confidentiality from the point of view of protecting models from being read by unauthorized parties while training on third-party computing facilities. So why is this important? Obviously, because training requires resources. I hope you also, well, I don't know if you noticed, but I mean, with certain settings, if you play around with this backprop, so it can be very time consuming. And modern large models, so they require data center to train them. So the idea is that you probably want to outsource training to some third-party facilities, to the cloud. But then, you have all these issues. So shall we send data in clear text? So what this cloud owner, how it will use it? Shall we and how can we protect the model itself, the neural network, to be trained in there? And so there are several attacks we try to be aware of in these settings, and basically invent mechanisms to mitigate the effect. So how practically we can mitigate these techniques is to maybe use trusted execution environments. So that's, I mean, that has little to do with machine learning models themselves. So basically, we talk about sandboxing the models and be able to verify that it is protected. We could think about a scenario where we where we distribute the learning, so that we instead of training a model on a single machine, so we instead train models locally with our data, and then probably we aggregate them in a single model, into a single model. In this case, we talk about federated learning. So federated learning will be the topic of Theory 3 module. What you can do as well, or actually what you probably want to do, maybe you want to encrypt your data. But the encryption actually doesn't really work here, if you think about it, because when you encrypt the data, so I don't know if you learned basics of cryptography, but in many cases, the output appears as totally random pattern. So basically, if you have a data, say again, MNIST images, all instances of number 7. So they look same to us. So same we have you remember we have this similarity measure, cosine similarity. So we can say, okay, yes, all 7s, they are close to each other, closer with respect to this measure compared to say 8. When you encrypt MNIST, so even a slight modification in a single pixel would result in totally random output. And as such, you cannot say, I mean, if you don't perform extra actions, you cannot use this data for training the model. So you either need to decrypt it and then kind of use it for training. But that's not good either, because you need to reveal your key. And the data will be at some point still revealed. Or you need to invent new techniques that actually perform computations on encrypted data. And this type of techniques is called homomorphic encryption techniques, meaning that you encrypt the text. So normally they are a class of homomorphic schemes. They belong to this public key crypto class. So you encrypt the data. So say 2 numbers. You add them together, so sum, and the encrypted text will appear the same as the sum, so the encrypted sum of the numbers that was encrypted before. So that is the idea with the homomorphic encryption. However, homomorphic encryption, it's still a challenge. So it's so practically useful schemes are very limited in functionality. So what we offer you to try is a different method, which is based on kind of obfuscation. So it's pseudo encryption, if you want. So, and this topic is discussed in the one of the papers I offered you to read, and to implement this method. And that's what I want to overview in the time remain. Well, someday maybe I want to start with this one. Somehow, well, it appears that this topic is directly connected to the research field I'm active in, which is called hyperdimensional computing. Well, again, there is a more formal way of introducing it using maths and such. But I mean, the main principles could be introduced on rather hand-waving level. So the idea is that for starters, so you remember I mentioned that in machine learning, data are high-dimensional vectors. So I mean, if you take this geometrical representation. But then high-dimensional spaces, they have very peculiar mathematical property. Now I say the kind of verbal interpretation of it. There is, of course, a math behind it. So high-dimensional space, so now pay attention, high-dimensional spaces are almost empty spaces. So think about it for this about this phrase a little bit. So what does it mean? So take this room as an example of 3D, right? So this is three-dimensional space. So and then so let's say any item in this place. Well, it's a point in our 3D space, right? So determined by X, Y, Z coordinates. And then we take any item at random and start to compute the distances to all other items that we observe here. The distances, by distances, I mean some maybe normalized distances, so that we have a limit between 0 and 1. So for example, cosine similar. So the cosine distance. So you compute them to all the objects, and obviously, so they are not 0, right, to any other objects in the class. So, and here we come to a very counterintuitive, maybe, case that when you increase the dimensionality of the space to several hundreds or even thousands, so which is the case for say reasonable size images. So you pick a particular point and you start to measure these distances to all possible points in this space. So which would be, I mean, astronomically many combinations. So you will find out that surprisingly enough, so all points will appear very, very far away and statistically concentrate around certain value. It means that so there are very, very few, like compared to this astronomically many points that are near you, and all other points they're very far away, and they concentrate around certain distance. So the whole space is virtually empty if you take a geometric interpretation. What does it mean? It means that on high-dimensional spaces, you can very easily generate orthogonal vectors. So, and orthogonality is one of the key properties when you want to create a cryptographic algorithm, for example. So you always aim at creating some random keys. So randomness is very important. So the idea here is that so you have your input. Well, in this case, it's two-dimensional images. And you just randomly generate a pattern of the same dimensionality. And then what you do, so you perform this operation, which is called 2D, two-dimensional Fourier transform. So again, the meaning of this operation is that you, so to say, crossover. So you overleave the two patterns. Maybe again, the best intuition would here would be if you take a binary case. So a binary case, again, let me just ask at least people who are sitting here. Did you have a course on cryptography? So do you know what one-time pad is? Huh? One-time pad is very simple and most powerful technique. So when you say, so it's a substitution cipher. So you have your text, block of text, and you generate a random pattern, substitution pattern. And again, so normally most of the algorithms, they work with binary patterns. So you do XOR, and the XOR inverts the bit positions basically. And if you do, so the same principle is virtually here. So this operation, which is two-dimensional Fourier transform or multiplication. So it plays pretty much same role as one-time pad. So when in binary would correspond to XORing two numbers. So here I mean, X and Y are real valued items. So, well, those images. And Y is generated randomly, X is your target. And this operation is called a convolution. So so you take two patterns and you slide them against each other in opposite direction, and then you produce, and the result would be basically the intersection between them. And this Fourier notation is because in a frequency domain. So the operation of convolution is implemented as component-wise multiplication. Again, that's not a goal for me to explain this Fourier transform, so you can read about it elsewhere. But again, the idea here is that you need an operation which corresponds to a one-time pad on real numbers, right? And this operation will be implemented by 2D Fourier transform. So how this scheme works? So you generate a secret of the same dimensionality as the output, and you perform this operation. Why it is not proper encryption? Because you see, with cryptography, in order to be qualified as cryptographic protection, you need to satisfy certain formal requirements. So this operation doesn't satisfy all of them. So you cannot say that this is an encryption. So sometimes this operation is called as pseudo encryption, or you could treat it as obfuscation technique. So, but the result is that you totally modify the input. So if you observe X hat, it has little to do, so it will appear as a random noise, basically. But the good thing is that this X hat will preserve exactly the same statistical patterns as X exhibit. So that you can basically take this X hat and build a model. And then when you build a model, you can do the inverse operation and retrieve the outputs of the computation. Yes, and basically, so maybe I can stop at this moment. In Canvas, I placed a link to YouTube, a recording of a talk presenting this paper. So you have the paper itself, and so the rest of questions we take online in Discord. unless you have some questions now in the chat. Well, if not, then I mean, with those of you in Skellefteå, so we take labs in the afternoon, and so you online, you will take the labs tomorrow and on Wednesday online. So I'm still here for another minute or so, so please feel free to ask questions. Well, if not, then see you. I see some of you on Wednesday. Have a good day. Bye.